Great. Thanks very much. So I'm going to start with, I'm afraid, a series of apologies. I have to make 3 apologies tonight. The first, Matt's already made for me, which is that, unfortunately, the conditions are not what we would like them to be for stargazing. And so, unfortunately, tonight we will not be going outside stargazing, but the Cambridge Astronomical Association will be giving us a planetarium talk instead afterwards. So you can see what we would have seen if the weather were better. The second apology, as Matt said, is from Calvin, who was meant to be giving this talk. As he mentioned, he's unfortunately ill, as seemingly everyone is this week. So I have been drafted in very sort of last minute, and that brings me on to the third apology, which is from me personally, which is that I haven't had a huge amount of time to prepare this. So I don't really have any slides. I'm going to be mostly doing stuff on the blackboard. So I'm glad you were that easily impressed. This bodes very well. And secondly, the second part of my apology is that, as you may have seen on the schedule, Calvin's talk was going to be 13 billion years in 30 minutes. I am unfortunately going to shortchange you a little bit. I'm still going to try and talk for 30 minutes if I can improvise that much to talk about. But I won't be talking about 13 billion years. I will probably only be talking about sort of 4.5-ish. So apologies for kind of cutting out sort of 2/3 of what Calvin might have been talking about. But one thing that Calvin might have been talking about is a very important principle for studying the universe on very large scales, as he does. He's a cosmologist, and that's what they do. This is a principle which underlies pretty much all of our study of the large-scale universe. It's really a very important one. It's known as the Copernican principle. And if I had to sum up the Copernican principle in 3 words, it would be, you're not special. That's the philosophy of it. More concretely, it means that no matter sort of where you are in the universe, there's no kind of special point. There's no direction in which we can look in the universe and see that everything gets sort of more dense. There's no sort of corner of the universe which is any sort of more special than anywhere else particularly. Obviously, when we look on smaller scales like the size of the galaxy, for example, the size of a planet, things are very inhomogeneous. We say there are local densities. But if you kind of smooth all those out and look on very large scales, there isn't very much separating one half of the universe from the other, or one direction from another. No matter which direction you look, you pretty much see the same number of galaxies. To give some context and talk about the history of the Copernican principle, I'm going to start by going back to ancient Greece and talk about a philosopher that you probably, I would be willing to bet, haven't heard of. So there's a kind of tier list of Greek philosophers, right? In the kind of top tier, you've got your Aristotle, right? Your Pythagoras, household names, your Plato, right? But then there is a tier below that of Greek philosophers who you might only have heard of if you have like a special interest in science or philosophy or whatever. And in that sort of second tier, I would put people like Eratosthenes, famous for measuring the circumference of the Earth for the first time, Euclid, people like this. But I think the philosopher that I'd like to talk about first sort of falls into a third tier. And I'd sort of like a show of hands. Has anybody heard of the philosopher Anaxagoras? Okay, we've got, I'm going to say fewer than 10 hands there, maybe fewer than 5. And understandably, Anaxagoras is not very, very well known. He was born around sort of 500 BC. I'll write his name so you can sort of see it. And as I say, it's about 500 BC. And I think it's kind of a pity that he's not better known, because he was the first philosopher really to make two very groundbreaking at the time, and also what turned out to be two very correct conjectures about the sun. So the first of Anaxagoras' conjectures about the sun is that the sun is larger than the Peloponnese region of Greece. That is, well, that's true. The sun is in fact larger than the entirety of Greece by quite some distance. So tick, bang on Anaxagoras on that one. But the second one might not have been that much more profound at the time, but certainly now it's more interesting, I think. Anaxagoras' second conjecture about the sun was that all of the stars in the night sky are objects that are basically like the sun. And he seems to, of course, we sort of know now that the sun is, just another star. But, in 500 BC, this was not necessarily obvious, right? If we're, walking around on this planet and there's this big bright thing in the sky and we can sort of see the kind of circumference, that we can see that it's an extended object, right? It's not just a point like all the stars are. I think it's not necessarily obvious that the sun would just be another star. So I think this is quite a leap of faith there. And of course, he turned out to be completely right. He did make some other proposals. So, for example, that the sun was made of basically just a hot ball of metal, which we know not to be true, but it was 500 BC, so I think we can cut him a bit of slack. But nonetheless, two very interesting and very correct conjectures. So this is very good. What Anaxagoras did not know, and I think what a lot of us, even people who are very interested in astronomy, don't tend to appreciate, is that although all of the stars are very similar objects, they all are powered by nuclear fusion, for example, there is actually a lot of variation among stars themselves. So, to give an example, does anyone know, shout it out, the brightest star in the night sky? Sirius, yes. So Sirius is, all right, it is about, right, some of you can see it. Sirius is a distance of about 8 light years away, or so. It's one of the closest stars to us, actually. So it's kind of understandable that it would be one of the brightest ones, given it's that close. Now there's another star, which you will all have probably seen if you've looked in the night sky, certainly if you spend most of your time in the northern hemisphere. And that star is called Deneb. Deneb is not quite as bright as Sirius. It's like the 19th brightest star in the sky, or about, I think it's the 9th in the northern hemisphere. It's very easy to see it on a clear night. We would certainly have been able to see it if it were clear tonight. It's quite high up, so it's quite easy to see. You can see it above, trees and things. And it is relatively bright. It's the brightest star in the constellation of Cygnus. So if you look up in the night sky and you see like a cross shape, that is probably Cygnus, the swan. And Deneb is a very bright star, and that's the head of the swan. Now Deneb isn't quite as bright as Sirius, but it is still pretty bright. It's, as I say, one of the brightest stars in the night sky. However, whereas Sirius is 8 light years away, Deneb is 2,550 light years away. And the reason that we can still see it, and it's still, almost as bright as Sirius, even though it's that much further away, is just because it is enormously bright. It's an example of a blue supergiant star, whereas Sirius is just basically a regular star. It's a bit hotter than the sun, but it's nothing particularly special. Deneb is a real monster, and we can see it almost as brightly as the brightest star in our sky, despite the fact that it's 300 times further away. But nonetheless, despite this basic difference, all stars do kind of run on the same machinery. They all are powered by nuclear fusion. They are all sort of the same kind of object. And so Anaxagoras is right in the sense, in that our sun isn't particularly special. And this is the first sort of time that someone has really described our position in the universe as not being anything particularly special. Because, if we have a sun and we think the sun is special, as all cultures do, there are countless others out there. The next time that someone has made a great leap forward in bringing about this idea of us not being in a particularly special location is I'm going to jump a bit further forward. So that's minus 500 BC. If I put the present day up here, over on this end, then the next philosopher that I'd like to talk about was running around in the 16th century. So that would be, right, so that's 2,500, so it would be about 60% the way along. So here, I'm going to talk about a philosopher called Giordano Bruno, who was an Italian philosopher during the Renaissance. I think he died in the year 1600. He was burned at the stake, and it will be clear why in a moment. Giordano Bruno had an idea that, and I think it's quite a relatively sort of intuitive and logical idea, that if, as Anaxagoras says, all of the other stars in the night sky are objects kind of like the sun, and if the sun has its family of planets around it, right? There are 8 planets in the solar system, and they all orbit around our star. Who's to say that all of those other stars out there don't have their own planets around them as well? Kind of stands to reason, right? The Catholic Church disagreed, unfortunately, and so yes, unfortunately, Bruno was burned at the stake in the year 1600. But this is again a profession of the idea that maybe there's nothing particularly special about our situation. Bruno didn't actually have any evidence that there were planets around other stars. This was just a sort of logical extension of Anaxagoras' idea, really, and the idea that the sun has several planets orbiting around it, which came from Copernicus, a sort of contemporary of Bruno's. But as I say, he didn't have any evidence of this. What I think is kind of crazy is that the first time that we actually found evidence of planets around another star came about here in the 90s. So in 1992, someone found planets around a very special type of star called a neutron star, and more specifically a pulsar. And then a few years later, in 1995, someone found planets around a more sort of normal, sort of sun-like star, for which they won the Nobel Prize. But I do think this is kind of insane that we've known since 500 BC, or we've theorized since 500 BC, that there are a huge number of places out there in the universe that are so similar to our own. But it's taken well within living memory, not for me, I was born in 2000, but well within living memory that the first planets were discovered. Many people in this room were born into a world where the only planets known to our species were the ones in our own solar system. And this is really indicative of the fact that this is a really, really exciting time in this field. So the field I'm in, I study exoplanets, which is a contraction of extrasolar planets, so planets around other stars. And this field has only existed for like 30 years. And we're already making some pretty incredible strides. In the sort of early 2000s, we managed to start imaging, like literally taking pictures of a solar system, around another star. We've been able to start characterizing the atmospheres of some of these planets. And it turns out, I think the most important thing we've discovered is that planets are everywhere. We think that pretty much every star has at least 1 or 2 planets in orbit around it. There are, in all likelihood, more planets than there are stars out there, which I think is kind of insane. If we look, in fact, to our nearest star system, so if we, the Earth and the Sun are there, our nearest star system is actually a triple system. So this is not to scale, but the nearest star system is called the Alpha Centauri system, and the nearest star in that system is called Proxima Centauri. There's a couple of interesting things about this system. First of all, it's a triple star system, and that's kind of interesting. It actually turns out that most of the stars in our galaxy are actually not alone. They're mostly in kind of interacting binary systems, or in this case, triple systems. It's actually, the Sun is relatively, I think something like 40% of all stars in the galaxy are actually just thought to be like the Sun and not have a binary companion, really the exception. We see most systems are actually in binary or higher order multiples. And secondly, just to, I've rubbed it off now, but to give the comparison of Sirius and Deneb, 2 very bright stars. Sirius was 8 light years away. This is 4 light years away, Proxima Centauri, and it's invisible to the naked eye. And even though it's twice as close as Sirius, we cannot see it because it's too faint. It's an example of a star called a red dwarf, which are much cooler and smaller than stars like the Sun. But again, red dwarfs actually turn out to be the majority of all of the stars in the night sky. And this one, we can't actually see it. So I kind of had a bit of an epiphany the other week when I realized that if you look out into the night sky, there are so many other stars there that you just kind of can't see. There are so many sort of stars in the gaps between the stars you can see that are just there. And this is an interesting point that's come up in terms of our habitability. So we orbit around a star that is not a red dwarf, so one of the rarer hot stars like the Sun. And some people have asked the question, why have we formed around a hotter star, a big hot star, rather than one of these very, very common smaller stars? Maybe there is something about these smaller stars which makes them less likely to be habitable, perhaps. But anyway, as I was saying, so the nearest star to us, we actually know does have a planet. We found a planet around it. We think there could be more, but we found one. We didn't have to look very far. We just had to look next door, and we found one. There, in the other 2 stars in the system are sort of a maybe. We've found some evidence of a planet. Some people have disagreed. So we're not really sure of that one yet. If we go a bit further out to another star, the next nearest star, Barnard's star, which is, I should draw it a bit further away, is about sort of 6 light years away or so. Barnard's star, I'll write it out. Barnard's star, discovered by Barnard, presumably. It's about 6 light years away. It's another of these red dwarf stars, very, very faint, not visible to the naked eye. Barnard's star has 4 known planets around it. Planets are just everywhere. It's crazy. But planets are really, really difficult to find in general. We've found, as of 2025, this year we've hit our 6,000th planet that we've discovered, which sounds like a lot until you think that we've discovered about 2 billion stars. So we've got some way to go in finding all of them. But it's just really, really difficult. There are, so as I say, we've found 6,000 planets. The majority of them, maybe 4,000 or 5,000 of them, were found essentially by luck. So the most successful method for finding planets is known as the transit method. So this method, what happens is you have your star, and if, and this is a big if, there is a planet orbiting it which just happens to take it in front of the star on its orbit. So if this is the star, this is the planet going around it. If it happens to pass in front of the star, then it will block out some of the starlight on regular intervals, like once every year for this planet. And then we will be able to see that. We don't have telescopes that are powerful enough to literally see this happening in most cases. All we can see is this star regularly getting dimmer for a bit as the planet passes in front. So this is a very popular method for discovering planets. It's discovered sort of 4,000 or 5,000, the majority of the ones we know. But it only works if the system is like this, if it orbits in front of its star. There's no reason for it to if we look at a random star, that its planet will be doing this. It could, for example, be doing, so this is a star. The planet could just be passing sort of around it. And if it's far away enough, if it's faint enough, then we just will not be able to see it. It's incredibly difficult because it won't block out its starlight. We can pretty much just see the star in almost all cases. And if it's going sort of around it on what we call low inclination orbit, then we just can't see it. But on the other hand, this does mean that there could be so many more planets out there than we've discovered. 6,000 so far, and most of them were lucky. So there are a huge number of stars out there for which we just don't know whether they have planets. And unfortunately, it's looking like we'll need a bit of a leap technologically before we'll be able to find planets around, any star you choose. The nearest stars, Proxima Centauri and Barnard's star, the planets there, they were relatively easy to find just because these stars are quite nearby and quite easy to discover. If we go further out, then it becomes more difficult and more harder to say whether we've discovered them or not. But yeah, it's a tricky game, but it's one that we're getting better at. And in particular, we're not just getting better at discovering planets, discovering new ones. We're also getting better at learning about the ones we already know about. So if our planet is like this, I'll get rid of this one because we can't really do anything with that. If our planet is like this and it passes in front of the star, then as I say, it will block out some of the star's light, and so it'll make the star appear a bit dimmer. Now, if the planet has an atmosphere around it, then when it passes in front of the star, some of the starlight will filter through the atmosphere of the planet. But the amount of light that filters through the atmosphere, it depends on a few things. So firstly, some molecules in the atmosphere absorb different colors of light. So if we see that when the planet passes in front of the star, certain colors of light are absorbed a lot more, then we can infer from that what molecules might be in the atmosphere of these planets. So this is a technique called transmission spectroscopy, and it's being used more and more these days to characterize what molecules are there in the atmospheres of the planet. And I do think that this is absolutely insane that this works, because some of these planets that we're able to do this for are hundreds of light years away, ridiculous distances. And we're talking about working out that some molecules, like molecules, have absorbed some of the starlight in between. So I think this is a technique which is a great victory of physics, really, that we're able to use these effects that the molecules have, which ultimately are due to quantum physics. And we're able to use that information, use what we've learned there to learn about planets on such a great distance away. Now, where are they just yet? One of the reasons that this has gained a lot of interest or notoriety, depending on who you are, is that recently, and I'm talking really very recently, I'm talking, like the last few years or so, we've been able to, that doesn't really work. Anyway, we've been able to use this technique to look for what are called biosignatures. So a biosignature is a gas that we might detect in the atmosphere of a planet, which is caused only, as far as we know, by life. So an example of this might be this is a chemical called dimethyl disulfide, or DMDS. And on Earth, the only thing that produces that molecule is phytoplankton in the Earth's oceans and us doing weird industrial stuff. There is no known, as we say, abiotic way, for example, through like geology or volcanic eruptions or stuff, to make that molecule. So, if we are looking at the light that is filtering through a planet's atmosphere, and we think that some of that light is being filtered due to molecules like that, these biosignature molecules, then we can think, well, maybe there's life there. And we are kind of able to do this now. It's very difficult, you need very intense observations, particularly a big player in this region is the James Webb Space Telescope, which has really pushed our ability to do this for the first time. But we now can. And one of the people who's kind of shown this is a professor here, a professor called Niku Madhusudan, who looked at a planet called K218b and found tentative evidence of a couple of molecules like this. People are arguing a lot at the moment about whether or not they found them or not. There's some evidence for them. But nonetheless, we've basically shown that it is possible now to find biosignatures in the atmospheres of other planets, which is an insane achievement for any kind of civilization to have accomplished. And I think it will only really raise further questions. And it means that we now sort of have to think about what would happen if we were to look at a planet and find an unambiguous biosignature. If we were to look at a planet and definitively go, okay, yeah, that molecule's there, something weird is going on, what would we do then? Well, as I said, these molecules are molecules that we, as far as we know, are only created by life. But maybe there is some very, very niche geochemical process which is able to create them. What do we, it might be difficult, but maybe it could happen. But I mean, in a sense, life is also a very complicated chemical process if you kind of boil down the biology. We are all just sort of chemical engines running at the moment. Where do you draw the line? Would a very, very advanced alien with a very, very complicated biology and a very complicated biochemistry look at our planet and see the biosignatures in our atmosphere and think, oh, that's just kind of normal chemistry that's happening, little people running around, that's just basic chemistry. Where do we draw the line there? And even if we do find life, I think it's very important to contextualize that and think about what kind of life would be most likely. So I've had this little timeline here. I'm now going to draw a parallel timeline. It's still going to end in 2025, but that will start, as I said, not 13 billion years ago, but 4.5 billion years ago. So this is roughly when the Earth formed. We know this through the timings from radioactive chemicals, radioactive atoms, which decay at very well-known times. particularly uranium, thorium, and lead, some lead isotopes which are radioactive. We know this number quite well. We know pretty accurately when the Earth formed, and it's roughly the same time as the Sun, it turns out. Now, going from 2025 back to 4.5 billion years ago, life hasn't existed for all of that time. The earliest evidence of life that we can find on Earth is about 3.7 billion years ago. So that's maybe about sort of here-ish. About 3.7 billion years ago. This is not particularly, we haven't found like an organism that's 3.7 billion years old in the fossil record or anything. We find very subtle variations in the numbers of isotopes of different carbon isotopes, and from this we infer that life must have been active in some little region of Australia or Greenland or something, in some rock somewhere 3.7 billion years ago. So for, a decent chunk of the Earth's history, it has just been lifeless. So in this period, most of which is called by geologists the Archean period, there is just sort of nothing. For a lot of it, the Earth would have been like molten, a lava world that had recently formed, and so it wouldn't really be suitable for life. The sun was also a lot hotter back in the day, potentially. There's still some debate about that. But it might not have been very suitable for life until we get to about here and things start to look a bit nicer. However, if we go back, the starting point of life at this time would have been very, very simple. It would have been just viruses and bacteria, basically. It wouldn't have been anything exciting. It wouldn't certainly be anything that would be an alien. What we would think of as an alien, right? When you think about aliens, you normally think of generally humanoid or certainly like animal species kind of running around, like big sort of macroscopic creatures. You wouldn't really think if you find like a bacteria on another planet. It would be a bit of a letdown, right? If someone said that they'd found aliens and it was just bacteria. But nonetheless, for pretty much the majority of of Earth's history, of life's history on Earth, it has just been that. We don't really get anything interesting, I can't remember when multicellular life happens, but macroscopic life happens around sort of here-ish. No, further, I think it's about here. About 550 million years ago. That's when life starts to look at least remotely interesting. You get these weird sort of, they look sort of like weird big leaves in the ocean. Life is almost entirely like in the ocean up to here, by the way. It's all these weird big sort of mat-looking creatures called Ediacarans. They're the first really kind of big life form that comes in. And then shortly afterwards, we have what's known as the Cambrian explosion, where life really, really starts to get going. Biodiversity explodes, and you get all sorts of things like crazy sharks and weird sort of shrimp things with funny beaks. It's a crazy time for life, just at the Cambrian explosion. But as I say, at this time, it's all still underwater. Life doesn't kind of emerge onto the land until maybe about here-ish. And the invention of the egg was very important in this process. So eggs were really fundamental in letting us sort of go on land. So the egg comes in around that time. Chickens, by the way, come in sort of around here. So that answers that question. If we think about an event in the history of life on Earth that we will have all probably heard about, then we might think about the dinosaurs and the extinction of the dinosaurs. Well, that was really very recent. Obviously, as we all know, 65 million years ago. That's maybe like somewhere there. So It's actually incredibly, incredibly recent when you think about the history of Earth, or even the history of life on Earth. It's very, very recent. I had a very interesting fact the other day, which was that if you were to imagine the history of the Earth, so 4.5 billion years, as 1 year, then the dinosaurs would have been wiped out on Christmas morning, which is an interesting fact. And it sort of says a lot about how distorted our view of life on Earth is, that everything since the dinosaurs is just compressed into that weird little week between Christmas and New Year's, where no one knows what's going on. That little week is pretty much everything we recognize as life, all of the mammal-dominated portion of it. The reason that I'm showing you that is that if we see, and it may well happen in our lifetimes, that someone finds some evidence of life on another planet, then we need to think about that in context. If there's an indication of life, in other words, a chemical in an atmosphere, well, if that would happen on Earth, that could be anywhere from here to here, right? It could be anywhere from 3.7 billion years ago, almost all of which would have been bacteria. So that is, and this is, I think, a slightly depressing realization, that is probably the most likely form of life that we would detect. It would, I think, have to take something quite remarkable, really, for us to be able to say, okay, there is an interesting species there, like something the size of a dog or something, which has only existed in sort of this range. And what we like to think of as intelligent life, which is a little bit controversial, because when people say intelligent life, they basically just mean humans. We like to say that we like to talk about different, like the human achievement of consciousness, as if like there was one gorilla that got born one day which happened to have consciousness even though its parents didn't, as if there was some switch that clicked, which seems unlikely. It seems more likely that there's a kind of gradation of consciousness. But anyway, this is 65 million years ago. I don't think I'm able to draw when books were invented, for example, or when the internet was invented. Everything we know, obviously, happens in a very, very small space of time. Now, if we are able to find, like, how long have we got?
No.
All right.
Wrap up soon?
All right, sure, yeah. Fine, yeah.
Very good.
Thank you. That's very kind of you. But another possibility is that we receive not a biosignature in an exoplanet atmosphere, but what's called a technosignature. So a technosignature is evidence of an advanced technological civilization somewhere. So this would be something like what's known as a Dyson sphere, where an advanced alien civilization is trying to harvest all of the energy from its star, and it does weird stuff to its star in order to harvest that. We might be able to detect that. But we sort of don't know, for obvious reasons, what life will look like beyond this, right? We know that the sun is going to burn out in sort of 5 billion years, so about twice as far away here. But we don't know what life is going to look like. It's certainly not going to be human, by the way. I think we do sometimes like to imagine that when the sun burns out, there will be some human sitting on a spaceship watching it. That will certainly not be the case. We will have evolved quite a lot in 5 billion years, if we're still around at all. And something that I try sort of not to think about is that maybe the reason we haven't really found any technological species that is trying to sort of communicate with us from beyond the stars, like we might be sort of capable of, is that requires a degree of technology which very quickly turns into a degree of technology which can wipe out life on a planet. So the kind of depressing possibility is that maybe you go immediately from developing some advanced technology to developing enough technology to destroy yourselves. So I can't remember what the name of that theory is, but there is a theory that the reason that we haven't found any contact with anything is because it is a necessity that technologically advanced civilizations will wipe themselves out through war or something. But let's not think about that. Let's. I'll wrap up on a lighter note than that, which is that as it stands today, and this might change, but as it stands today, this is the only place in the universe where we know that life exists. There are a lot of prerequisites. There's a lot that you need for life to exist, and all the conditions are here. So we're kind of lucky in that sense. But I think we're also lucky alive at this moment in time. Because as I say, this is the first time in the history of our civilization that we are capable of detecting life elsewhere. We haven't yet, but that could be about to change. So, maybe we are special after all. Thank you very much.
Fantastic. Life, the universe, and everything. Do you have any questions for our speaker? Please, yes.
What did you think about NASA's press conference recently about that perhaps they found some signs of life on Mars?
People argue about this a lot. I think so pretty much nobody is saying that there is life on Mars now. I think it's fair to say that that's not really a possibility just because Mars is so inhospitable, so cold, no liquid water anywhere convenient, all that stuff. But what people are increasingly looking at is the possibility that life may have existed in the past, and we're finding a lot more evidence now that I think it's pretty certain that there was kind of liquid water in the past. So we see lots of like what sort of look like river systems, right? I think there's not enough evidence yet to say that there was life. If there were, then we're getting closer to being able to make the measurements we would need to tell that. So similar measurements actually that we use to tell that when life started on Earth. But I don't think we're there yet. But it's definitely a space to watch. And to give my personal opinion, I think it's probably more likely that we will find life in our own solar system before we find life outside of it. Just because it seems like we're in quite a special solar system.
The front, please.
You mentioned 6,000 exoplanets.
Yes.
4,000 by the transition.
Yes.
So how are the other 2,000 been?
So there are a couple of ways the others have been found. One of them is through direct imaging. So in a small number of cases, it is actually possible, even in this scenario. If the star is sufficiently nearby and sufficiently young, and the reason that's important is because it means that this planet hasn't cooled down yet. And if the planets are sufficiently big that they are still bright enough, then we can sometimes spot them by direct imaging. Another possibility is that if your planet is orbiting in a not quite transiting configuration, but maybe it's slightly tilted. It's not orbiting, this is not in the plane, this is like maybe I'll draw this thicker on this side to indicate that this is sort of going into the plane of the paper, so this would be sort of like that. Then actually the gravitational pull of the planet on the star actually is slightly significant, and sometimes it can cause the star to kind of wobble around a bit as well. And we can actually detect the motion of the star moving backwards and forwards as a result of the gravitational pull of the planet. So this is this so-called radial velocity technique has also been used to discover quite a lot of planets.
That's the two that the other 2,000 would have been detected
Most of them, yeah. There are a few more sort of niche methods, and people are coming up with newer, nicher methods all the time. But yeah, those are the main ones. Yeah.
You mentioned the bisulfide molecule. What about phosgene? Is that a no-no now on Venus? Isn't it?
So phosphine, I think, is that one. So that was a molecule called phosphine, which looks like that, pH 3. I think people generally agree now that that actually probably isn't there. I think that there are a few different people who claimed that they measured this molecule there, and a few people after that who claimed that they didn't and reanalyzed the data in different ways and didn't find this. But there is also a lot we don't understand about the chemistry of Venus. Venus is quite odd. It's so similar to the Earth and yet so different. It's like sulfuric acid clouds in the atmosphere. It's closer to the sun, so the sun has more of a role in it. It's a really very complicated place. So we think that that probably isn't there, but it still could be. I think it's just very difficult to tell, even though you know it's right there. There are a number of missions to Venus planned over the next couple of decades, which will hopefully clear it up. But yeah, I think the jury's still out on that one at the moment.
And we'll do a couple more for the tea break. We'll just start with you.
So what's the advance in the technology that makes it possible now to see these planets? Because I would think of optical methods as something that's very traditional, old, sort of maxed out. Very much like we know wavelengths, we know the speed of light, we know telescopes, we've done everything there is. And all the modern technologies from AI over computer things and chemical things we cannot apply over these distances, right? So what's new?
What's new? There's a few things. I think partly it's in computing power, so partly we have a greater ability to make use of all of the data we can get. If we get a lot of data on a certain object, that makes it easier to confirm or deny these. Partly it's about rocketry. So the James Webb Space Telescope, for example, is really, really big for a space telescope. It's like 8 meters across or something?
6.5.
6.5, right. And it took a lot of engineering to get that into space. It took a lot of engineering to get that just in a rocket on the ground, let alone to send that all the way up. I think another thing is material science. So a lot of these detectors that are used are more sensitive not to visible light but to infrared light. And the infrared can be quite a difficult wavelength range to make chemicals to be able to absorb them properly and in a way which we can understand. So yeah, some very interesting material science has gone on in the sort of construction of these telescopes to be able to collect the data that we need.
Fantastic. And we'll do a final question here before the break.
If the sun moved any closer to the Earth, would the Earth like crumble like into pieces and we all like burn?
Probably we would burn first. And then crumble a bit later, depending on how close we went. So if the sun were a lot closer, then yes, everything would get hotter. Life would very quickly become very difficult. The people talk sometimes about the habitable zone, which is the range of distances from the sun that a planet like the Earth could reasonably survive in. The inner edge of the habitable zone is actually really quite close to where we are. The outer edge of the habitable zone, I think Mars might technically be in the habitable zone. The only reason Mars isn't inhabitable is because it's lighter and so it doesn't have an atmosphere. But if Earth were like a little bit closer, then life probably wouldn't be possible. If you take Earth a little bit inwards, then you would get loads of forest fires and everything would burn. But if you took Earth a lot closer to the sun, I forget exactly how close, but then the gravitational force hang on, I'll draw this out. So if you have the sun here and the Earth alarmingly close like this, I'd say not to scale, but maybe this is to scale. Then the gravitational force on this side of the Earth would be so much bigger than the gravitational force on this side of the Earth that the sun would just be able to kind of rip the Earth apart like that.
Like split it in half.
Probably not split it in half. What would probably happen is all of the sort of mountains and the highest up things would have like rocks stripped off the top of them first. So it would probably get broken, not in half, but maybe like this bit would come off first, and then this bit would come off, and then it would all sort of crack in layers like that. That's probably how it would happen, yeah.
I think, didn't we find something like that? There's a planet which is this sort of funky egg shape, because, as Sam just said, it's so close to its star, it's in the process of being torn apart by its star's gravity.
Yeah. There's a gas giant planet which is sort of like that. So this would be sort of the circular, what it would look like if it was a circle. And the star is just pulling on the gas on the inside. So it orbits sort of around like this in this sort of egg shape. So the near side is kind of pulling some of the gas around in there like that.
Okay, we've reached the destruction of the world, which I think means it's time for
Time for tea.